And then I can show you some interesting case studies. You can see that we actually show you these two cases. So one is just a 12-bus system. The other is a real 40-bus system. And both have the secondary network or secondary system modeled, so we can do this analysis. And we run different scenarios. In most scenarios, except for the second scenarios, basic means there's no solar injection. I mean, there's no solar penetration in the training side. So that means they haven't seen any solar when we train the model, except for the scenario 2, we give them a very low solar penetration. And then we do the testing. But when we do the testing, we have different levels of solar. So this is trying to see, okay, the under different penetration levels, when we do the testing, so how the system perform. Because when you do the testing, when you have solar, you're trying to deal with some unseen scenarios for during your training period, right? And then we show you the result. Basically, we want to estimate the voltage, under different solar injections. Okay, so this shows you the voltage estimation errors with different test cases, 12 bus, 40 bus I show you, and there's April Circle 5. This is thousands of buses. So you can see that for different method, including the fixed informed neural network I just showed you, we specifically designed the neural network structure, and just the DNN means we only we do not consider any physics. It's basically just a black box model, input output. Or LNN, that means we do not consider that linearization error module, or we do not consider that compensation module, and what's the result. So clearly you can see the result and the performance for different method, especially under high solar penetrations. Under high solar penetrations, which is scenario 5, you will see that every method tend to perform worse, but actually the physics one will perform much better than the other two, because you consider the physics. That means you have a much better extrapolation capability, and even for unseen scenarios. So that's a main point, because you want to predict the future. Okay, so I think this is a very brief. What I want to show you here is that it's not a complete picture, because eventually we're gonna to translate this into the solar hosting capacity metrics, right? But this is one criteria to decide that solar hosting capacity, because you want to see, okay, how much voltage variation under different solar penetration level. To do this, you use this neural network to find the sensitivity, the voltage to PQ injection sensitivity at each node for each customer. And then you can use that sensitivity to somehow predict, okay, under different solar penetration level, what are the potential voltage variations. And then depending on how how tolerant you are to those voltage variations, you can decide the solar hosting capacity limit. Okay, I just want to explain to you why this matters to the solar hosting capacity analysis, especially model-free solar hosting capacity analysis, because we assume we only have smart meter data and we don't have the system topology, and we don't need that.